Okay, so we saw uh, the remainder theorem. That is, when we divide a polynomial of degree greater than or equal to 1 by a linear polynomial, to find the remainder, all we have to do is we have to find out what is the 0 of the divisor. If the 0 of the divisor is a, then the remainder will be p of a, where p of x is the dividend. For example, this is why this theorem helps us. One example where this theorem is useful is find the remainder when x to the power 4 plus x cube minus 2x square plus x plus 1 is divided by x minus 1. So if we do this with the long division process, it will take so much of time. So instead of that, what we can do is we find what is the divisor. Okay, we find out what is the 0 of the divisor. So the 0 of x minus 1 is 1. What do we have to do? We have to substitute 1 in the dividend. So p of 1 will be 1 to the power 4, 1 cube minus 2 into 1 square plus 1 plus 1, and that will be 2. So the remainder when p of x is divided by x minus 1 will be p of 1, and that is 2. So this is true because of the remainder theorem. So in this way, remainder theorem helps us to calculate the remainder, okay, of polynomials which are divided by linear polynomials easily without using the long division method. Another example is check whether the polynomial 4t cube plus 4t square minus t minus 1 is a multiple of 2t plus 1. Okay, so how do we check whether? So check whether 24 is a multiple of 3. So is it a multiple of 3? Yes, because 8 times 3 is 24. So 24 is a multiple of 3. So what happens when the numbers are very large? Okay, suppose one example like 2, 2, 4, 5, 6, 8. How do we check whether it is a multiple of 3 or a multiple of 8? Okay, so another way of solving this is when 24 is divided by 3, the remainder is 0. Okay, so suppose, as I said before, I want to check whether 845 is a multiple of 7. For smaller numbers, we know the multiplication table and it is easy for us to find out or to do mental math. But for bigger numbers, how do I check whether this is a multiple of 7? I can't write the whole multiplication table up to 800. So what do? I have to check whether the remainder is 0 when 845 is divided by 7. If it is a multiple of 7, the remainder will be 0. So in this question, I have to check whether this polynomial 4t cube plus 4t square minus t minus 1 is a multiple of 2t plus 1. So what do I have to do? I have to check whether the remainder is 0 when q of t is divided by 2t plus 1. So there are two ways of doing this. One way is the long division method, but we know that that will take so much time. So what do? We can use the remainder theorem. So q of t will be a multiple of 2t plus 1 only if 2t plus 1 divides qt, leaving a remainder 0. So here we have the linear polynomial. Okay, now to find the remainder, what do? I have to find the 0 of the divisor. So first I equate it to 0, then I solve for t. So t is equal to minus 1 by 2 is the 0 of the divisor, which is 2t plus 1. So now I substitute the 0 of the divisor in the dividend, which is q of t. So q of t is 4t cube plus 4t square minus t minus 1. So minus 1 by 2 is the 0 of 2t plus 1. So what will be we'll be having 4 into minus 1 by 2 cube plus 4 into minus 1 by 2 square minus minus 1 by 2 minus 1. Okay, 4 into minus 1 by 2 cube plus 4 into, instead of t square we have minus 1 by 2 square minus t will be minus of minus 1 by 2 and we'll have minus 1, and simplifying this we'll have minus 1 by 2 plus 1, and minus of minus 1 by 2 is 1 by 2, and then we have a minus 1. Minus 1 minus 1 plus 1 minus 1 cancels, minus 1 by 2 plus 1 by 2 cancels, and that gives us 0. So the remainder, and this q of minus 1 by 2 is actually the value of the remainder when q of t is divided by 2t plus 1. So since the value of the remainder is 0, it means q of t is a multiple of 2t plus 1. Okay. So the remainder theorem, can we say it will be true for all polynomials? So do we have any proof for that theorem? So now we'll be looking at why the remainder theorem is true, or the proof of the remainder theorem. So first let us look at what we know. We have learned the division of numbers. We have the dividend, divisor, quotient and remainder. And we know that dividend is quotient into divisor plus remainder. That is 223 is 74 times 3 plus the remainder. And we know that we stop the process when all the numbers in the dividend are used up and when the remainder is less than the divisor. Okay, when the remainder is less than the divisor. So as we saw in the other examples, we can divide two polynomials. So I am dividing p of x by some other polynomial g of x. Then I'll get a quotient q of x and a remainder r of x. So here I got just a constant 3. I can get maybe 3x or 3x plus 2. As the polynomials in the dividend and the divisors, as they change, the q of x and r of x also changes. So upon dividing a polynomial p of x by a polynomial g of x, we'll get a quotient polynomial q of x and a remainder polynomial r of x. Okay. So we saw that dividend is quotient into divisor plus remainder. So the same thing I can tell in the case of polynomials also. Dividend, okay, p of x is equal to quotient into divisor. Quotient is q of x into g of x plus the remainder is r of x. So I can write p of x is q of x times g of x plus r of x. In earlier case we saw that the remainder is less than the divisor. The remainder was less than the divisor. But when it comes to polynomials, what do we say? We change it to degree of the remainder, or degree of r of x has to be less than degree of the divisor. Okay. So in the case of numbers, we know that we can divide two numbers, equal numbers, that is the divisor and the dividend are the same. We can divide two numbers where the divisor is less than the dividend. Here the divisor is 2, the dividend is 10. So the divisor is less than the dividend. We can do it the other way also, that is 2 divided by 10 is also possible. that is the dividend is less than the divisor. But in the case of polynomials, okay, the first situation is possible. You can divide p of x by p of x, that will give us 1 and the remainder will be 0. But the third uh, option is not possible. That is, the degree of the divisor must be always less than or equal to degree of the dividend. We cannot have degree of the dividend less than the divisor. Okay, so the degree of the divisor must be always less than or equal to degree of the dividend. Okay, that is degree of g of x must be always less than or equal to degree of p of x. So if the p of x term is x square, okay, the g of x term can take some x power 0 is possible, x power 1 is possible, x power 2 is also possible, but it should not go above the degree of the dividend. In this case, it is x square. So x power 3 is not possible. So what have we seen in the past two slides? I'm sorry. If p of x and g of x are two polynomials such that degree of p of x must be greater than or equal to degree of g of x, that is degree of the dividend must be always greater than or equal to degree of the divisor, and the divisor must be not 0, because dividing by 0 we get the answer will be uh, not determined, because any number by 0 is not defined. So g of x or our divisor, it should not be 0. And then if we divide p of x by g of x, we can find polynomials q of x and r of x. So we have the quotient and the remainder such that p of x is g of x into q of x plus r of x. That is, the dividend is quotient into divisor plus a remainder, where the remainder can be 0. When does it become 0? When g of x is when p of x is a multiple of g of x, or the degree of the remainder has to be strictly less than uh, the degree of g of x. See here, less than or equal to is also not possible. It has to be less than. So degree of the remainder must be less than degree of the divisor. Here we say that p of x is divided by g of x, and it gives the quotient q of x and the remainder as r of x. So now let us look at the proof of the remainder theorem. So when p of x is divided by q of x, we know that dividend is quotient into divisor plus remainder, and the degree of the remainder is strictly less than or less than the degree of the divisor. Okay, so the remainder theorem says if p of x is divided by a linear polynomial x minus a, okay, where a is any real number, the remainder is p of a. Okay, so now g of x here is x minus a, the linear polynomial, and the 0 of g of x is x is equal to a. That is, when we substitute a instead of x, we get g of a is 0. So g of x is a linear polynomial, that is, the degree of g of x is 1. Degree of r of x must be less than degree of g of x. So this is 1. So if it has to be less than 1, degree of r of x must be 0, which means the r of x is a constant, some number r. So this will be p of x is equal to g of x into q of x plus some number r. So when we substitute the 0 here, this term, that is g of a, becomes 0.